Now let me start talking about MM1 queuing system. MM1 queuing system is by Kendall's notation MM1. The first M is trying to denote the Poisson arrival because it has exponential distribution for the inter-arrival time. And second M is for service time distribution. Service time distribution also has memories property, which means service time is supposed to have exponential distribution. And the third notation here, the one is actually trying to denote that it's trying to represent the single server. So there is only one server here, and we're supposed to have actually infinity here, right? In the Kendall's notation, but it's usually we leave it out. So infinite here means we have infinite capacity, actually infinite, no limitation on capacity. Okay, infinite number of customers can wait in the queue. So this simple queuing system, we have arrival, which is actually Poisson with the mean of lambda, and we have the exponential service time distribution with service radius mu, which means average service time is 1 over mu, and average inter-arrival time is 1 over lambda. And inter-arrival time is supposed to have an exponential PDF like this, okay, with the rate lambda, mean rate lambda, and the service time okay, supposed to follow the exponential distribution given by service rate of mu, which means average service time will be 1 over mu, single server. And as far as the scheduling is concerned, okay, scheduling, we need a scheduling discipline here. Scheduling discipline can be actually arbitrarily. It can be anything. Okay, it can be first come first served. That actually, as far as the MM1 queuing system is concerned, okay, we don't care about any kind of scheduling scheme. Okay, given this simple model, what we're interested in is the system size. Okay, what I mean by system size is the number of customers in system. Okay, so let me use the notation S of t, which is to try to note the number of customers in the system at time t. So this is the number of customer will be the system size. Okay, so we're trying to find out all about the S of t. For example, we want to find out the expected value of the S of t. What is the average system size? So we need to, if we do know the distribution of S of t, we can find many different things like average queue size, average waiting time, and so on. Okay, so the distribution of S of t is, I think, almost important thing to drive first. So we need to know that the distribution of S of t. So let me use P sub n of t to denote the probability that system size is equal to n when time is t. Okay, so this time axis, and at time t, you're going to have S of t. Okay, the number of the S of t is the number of customers in the system at this time. So there will be a lot of arrivals at arbitrary times. There will be a lot of arrivals, and if you look at the system at time t, the total number of customers in the system will be S of t. So the first thing is to find this distribution of S of t. Okay, once you know the P sub n of t, this particular distribution, okay, you must be able to find many other quantities later on, including the waiting time. So in order to find the P sub n of t, the distribution for the system size, so at time t system size n, okay, this is distribution, right? In order to find this, we need to make observation for the system. Okay, let's focus on the arrival probabilities. Okay, well, you might want to answer to these questions. What is probability of one arrival in this short interval delta t, with the length of the delta t? Actually, we have time t, time axis and t, and t plus delta t. So you have a short interval of delta t, and you are interested in how many arrivals are you expecting in this short interval. And remember that this arrival is supposed to be Poisson, right? Because inter-arrival times is assumed to be exponential, right? So by definition of Poisson process, actually, we are expecting okay, 0 or 1 arrivals, no more than one arrival during the short interval delta t, right? We're assuming that delta is very close to 0. So as we discussed earlier, one arrival, okay, probability have of the one arrival during this interval as probability of one arrival during this interval is lambda times delta t with the correction factor little of delta t, and 1 minus this probability is probability that there is no arrival, right? So 1 minus delta t plus little o. Okay, and we're not going to have more than one arrival, right? So it's going to be 0, but actually it's little of delta t to make it equal to, okay, so it's very close to 0, right? Okay, and this is all about all the probabilities concerning the arrivals. Okay, and how about departures? Okay, well, okay, let me take a look at the timeline again. Okay, there is time t. Okay, the service is not okay. Okay, we have t plus delta t. Again, I have a short interval here, delta t, interval of delta t, and by time t, actually, no one has, I mean, the service has not completed yet, which means, okay, service is still going on, and then I'm interested in finding the probability that the service is completed in over this interval of delta t. So departure over here, okay, service is completed and it depart the system, right? So what is probability that the customer leave, okay, time between t and t plus delta t, or in this interval, right? So that's the probability I like to find out. So this is a conditional probability, right? In the sense that, okay, service is not completed. Service has not been, okay, finished yet by time t. So again, okay, the service time is supposed to have memories property. That means we don't care about, okay, remember the memories property. We don't care about how long it has been served, right? So only thing we have to worry about is this the time interval delta t, right? So the departure, okay, the probability they depart, okay, this short period, very short period, right? So during short period, actually none is leaving or only one is leaving, right? No more than one customers will serve, right, during the the short interval of delta t. So probability that only one customer is served, okay, is departure rate times the time delta t, right? And then 1 minus mu delta t, okay, will be the probability that no one is served, right? And again, okay, more than one service, okay, more than one customers are served, okay, during this interval, okay, it will be actually is equal to little of delta t, right? Because there will be at most one customer will be served during a short interval of delta t. Okay, so these are the probabilities of concerning the departure. So we have arrival probability as departure probability. Using these probabilities, I can drive this distribution for the system size. Well, by the way, the one important system parameter over here is actually lambda and mu, right? If I give you the average, if you know what the average arrival rate is, you know what the lambda is. Lambda is, you know what the distribution of arrival, inter-arrival will be, and if I give you the mu, the service rate, you know what the service time distribution will be, right? Because all these are exponential distributions, so exponential distribution will follow the only these parameters, lambda and mu. Well, anyways, you will see that after analyzing the system, you'll find that the system, okay, the behavior system depends on lambda and mu, and especially not just independently lambda and mu, just actually the ratio, okay, lambda and mu. Actually, lambda over mu, which is denoted by rho. Okay, rho is actually important, the parameter that governs the system behavior. So let me use rotation rho, which is defined as lambda over mu, and it's called the traffic intensity. So think about this, okay? Mu increases. What happens? Actually, lambda increases and mu decreases, then rho increases, right? Lambda increases means more more and more actually customers coming in. Arrival rate is high, getting higher and higher. So system is getting congested, right? But thing is, depending on mu, okay, if mu is service rate, right? How many customers will be served within a second? And if mu is small, and so actually this is not true, right? If mu increases, okay, if mu increases, what happens? Actually, the service rate is high means everybody get a faster service, right? Service time is getting smaller and smaller, right? Because the number of customers that is leaving the system after service will be increased, right? Okay, so mu is service rate. How many customers will be served within a second, right? So either lambda is increased, lambda is increased, and mu is increased, then okay, well, if mu is increased, actually the traffic intensity will be actually the reduced. Okay, well, this is what it is. Okay, lambda times 1 over mu means, okay, what is 1 over mu? 1 over mu is actually average service time, right? Average service time. And lambda is okay, this average service time, this is actually the second, right? Okay, 1 over mu second it takes on the average. And the lambda is actually number of customers per second, right? Number of customers in second. Okay, every 1 second, how many customers you have? So if you multiply lambda by 1 over mu, that's actually tells you the number of customers during the average service time. During time interval of 1 over mu, on the average, okay, actually the lambda times 1 over mu will be average number of the customers that has been that have arrived in the system, right? So if given lambda, okay, given mu, okay, once the service time is average service time is fixed, then as the higher the average arrival rate is, the higher the traffic intensity, the higher the load supposed to be, right? Or if mu is really large, okay, large mu means actually you have very shorter interarrival, I mean the service time, right? If mu increases, actually the average service time is very small, right? Okay, the higher service rate means, okay, the shorter service time. The shorter service time implies that the number of customers that is arriving during this interval will be smaller, right? So if as lambda increases, I mean mu increases, okay, if mu increases, actually rho actually decreases, traffic intensity decreases, right? Because you have actually less number of the arrivals during this interval. Okay, so combining lambda and mu together by this relationship, lambda over mu is going to tell you, okay, how intensive traffic is in the system, right? Okay, all right. Okay, think about this. If lambda over mu is greater than 1, okay, so actually, okay, well, by my interpretation over there, okay, if lambda times 1 over mu, okay, if this is greater than 1, then what happens? Actually, okay, 1 over mu is average interarrival time, I mean service time, right? During the service time, actually, my arrival is actually more than 1, right? So serving, okay, when I'm serving one customer during 1 over mu, I'm arriving more than one user, more than one customer. So my capacity, my server, okay, has a capability of serving only 1 over mu, okay, only 1 over mu customer per second. Oh, I'm sorry, one mu customers, right? Well, mu customer, or during this time, okay, 1 over mu, okay, during this service time for the one specific customer, okay, while serving only one customer, I'm having lambda, okay, lambda arrivals, and actually so during this time, if arrival rate is lambda, it's altogether, okay, this is going to be number of, as I said, this is number of customers, okay, number of customers arriving during serving only one particular customers. So in case this is greater than one, then system is really congested because server is too busy, right? While serving one customer, you're expecting more than one customer arriving. So that's very busy system, right? Actually, the system will be eventually explode because too many customers coming in, and you are actually the capability of the server is very limited, right? Okay, limited in the sense that you have too many customers, okay, arriving. So traffic intensive is greater than one, then the system is going to blow up. The system will actually cannot be stable at all, right? So we have to assume that rho is always less than one. Okay, so in other words, arrival rate must be always less than service rate. This is the assumption we need. Otherwise, okay, if lambda is greater than mu, arrival rate is greater than service rate, then you're in trouble, right? This is very intuitive, right? Okay, in the previous page we have found all the probabilities for the arrivals. Okay, probability. Okay, we have looked at actually two intervals, right? Actually, t 0 to t and actually t plus delta t, and so this little interval, okay, the little interval from t to t plus delta t during the short interval, okay, during short interval probability that there will be actually either is no arrival or one, right? Either 0 or 1. So probability that one arrival, probability of no arrival, and of course probability of more than one arrival would be 0, right? I mean almost equals 0, right? And one arrival lambda times delta t, otherwise 1 minus lambda delta t. So we found the probability of all the arrivals, and also we found the probability of service completion, right, during this interval. So mu times delta t, and of course, okay, you're not going to have more than two customers served at the same time during the interval. So this gotta be almost equal 0, right? So we found all these probabilities in the previous page. Given these probabilities, what we're interested in is we want to find out the distribution of system size. Actually, we have system size at the time t plus delta t, and also system size at time s of t. Okay, so probability of we have actually we have n customers at time t plus delta t, okay, which is over here. At time t plus delta t, say we have n, okay. Then actually at time t we could have only we also had n or n minus 1, right? We can't have n minus 2 because if we had n minus 2 customers at time t, we should have 2 arrivals during interval delta t, so that we can have n customers at time t plus delta t. So we're not going to n minus 2 or n minus 3. All these are not going to happen. So we only consider only 2 cases, right? When we have n customers at time t and n minus 1 customers at time t. So this probability, okay, will be same as this, right? You had n at time t, and then if no arrivals, and also you have to consider departure, right? Okay, if there is one departure there, then actually you're going to have n minus 1, right? You're starting with the n at time t, and then if there's departure, okay, you're going to have n minus 1 at time t plus delta t. But we want to find the probability that you have n customers at time t plus t delta t. So you're not supposed to have any arrival and no departure, right? During this interval, right? Or you had n, and you had a one arrival and one departure. So nothing happens, right? I mean, one arrival, one departure. That means you still the number of customers in the system is n, right? Or you had n plus 1, and then no arrival, no one departure. Okay, right? If you do have like one arrival, then it's kind of n plus 2, and the one departure is kind of n plus 1, right? Still, it's not going to be n. So n plus 1 and no arrival and no one departure will give you the n customers in the system. Or n minus 1 customers, okay, and then one arrival and no departure. So you go to state n, right? So we have state n minus 1, we have n customers, right? There's transition, right? Okay, we're talking about transition from n minus 1 to n, right? and 4 different events, right? 4 different events. Okay. No arrival, no departure. One arrival, one departure. No arrival, one departure, and one arrival, no departure. Right? Or actually, like this, right? Okay, state transition. Okay, I'm sorry. Let me rephrase it. Okay, n-1 to n. Actually, we have one arrival and one departure, right? That's one. Okay, one arrival, one departure, no departure. And okay, there is also transition that n+1 to n, right? When no arrival, one departure, then you go to n+1 to n. And then from n to n, right? No arrival, no departure, no arrival, no departure, and one arrival, one departure will also give you the n to n, right? So you have all kind of transitions, state transitions here. Now, okay, having said that, you want to find all these probabilities, right? So the first probability over here, okay, okay. First of all, you have to think about, okay, you had okay, this is a probability that you have n customers at time t, and then whatever happens during the time between t and t plus delta will be independent, right? Okay, so this actually the whatever happening during the short interval delta t is independent of the number of customers you had at time t. So it's all independent. Okay, so the probability of probability s is n, probability of s is equal to n, or a probability of s is n+1, n-1. Okay, so all these are independent. So I have probability multiplied by, okay, because of the independence, right? And then no arrival, no departure means, okay, so when you have n in the system, okay, so and then you have to think about the conditional probability, right? Because you multiply by this, so this is actually conditional probability times this will be actually a total probability, right? I mean, not the total probability, the joint probability, right? So joint probability will be actually this probability times the conditional probability will give you the joint probability. And so when you had n customer in the system, and no arrival, no departure during this interval is actually, okay, the arrival and departure is also independent, right? So if you look at, okay, actually I'm rewriting everything here on the right hand side. So this is actually a probability that there is no arrival, and also there's going to be probability there is no departure. Okay, when you think about the departure, okay, you need to keep the condition. For the arrival, you don't have to think about the condition, because the arrival is independent of the system state, right? No matter how many customers you have in the system, okay, the arrival process doesn't care, right? How many you have in the system. But departure, okay, the number of customers in the system matters, right? For the departure. If you don't have anything, you don't have any customer in the system, then there is no departure at all, right? The departure actually depends on the whether you have customer in the system or not, right? So that's why, okay, you have independence, okay, the arrival process and departure is independent, and for the departure, you need to consider the condition, okay, condition for the system size at the beginning. Okay, so and then the second probability over here, right? It's a one arrival, one departure. Okay, well, this is a one arrival probability for the one arrival, and then you have to multiply by the one departure, right? Okay, given this state. And same thing goes here, right? The third one, okay, there's probability over here, okay, actually, okay, these are the probability of the state, state n, and that is state n+1, and then no arrival, which means 1 minus lambda t, and one departure, right? Okay, and now the system is n+1, right? And same thing goes here, okay, when system is n-1, this is probability of system when system is n-1 times one arrivals, which is lambda delta t, right, times, okay, no departure during the interval given that system state is n-1. Okay, and we know, okay, we got all these probabilities, right? All these probabilities, and no departure, okay, no departure during this given this state is actually no departure is 1 minus lambda t, I mean mu delta t. One departure is mu delta t, one departure mu delta t, no departure is 1 minus mu delta t, right? And then at the end, okay, I put actually correction factor. Everything is approximation. This is approximation, supposed to be approximation, right? But if you want to make it equal, okay, you want to put the little o, right? Okay, so if delta t is going approaches 0, okay, this one go to 0, and it's going to be really equal to each other, right? So now I have this uh, the uh, this probability at time t plus delta t has uh, given by some of these different probabilities, and I can actually okay, this is probability we just derived, we just looked at, and you can actually expand these terms, and maybe like you multiply each term by each other. Okay, like you multiply all these terms. Actually, you're gonna multiply like lambda delta t and mu delta t. You multiply like this, and you're gonna have like a delta t squared, but this is still very small number, right? Delta is small, and delta t is very small, and if you square it, it's gonna be still 0, right? Almost very equal to 0, right? So I can say this is actually this one is equal to liter of delta t, right? Right. Okay, so this one is also like p times literal of delta t. Okay, in the course of expanding these terms, okay, you're gonna have p sub n multiplied by literal of delta t. It's gonna be still very small, right? Because literal of delta t is small, probability is less than 1, so it's still very close to 0, right? So this constant, actually constant times literal of delta t. I mean, any constant multiplied by literal of delta t will be very small, right? Because literal of delta t is very small, close to 0, right? Okay, of course this is true, right? If you square that, the literal of delta t is literal of delta t. So anyways, using these observations, you can actually simplify this expression. Okay, this one is equal to this, and this one, okay, actually can be rearranged. All these things will be simplified into this difference equation. Okay, and then once you have difference equation like this, you divide it by delta t. Delta t will be divided. Okay, and then this one delta divided by delta t, and then you take a limit. Okay, let the delta t go 0, and this literal thing will be equal to 0, and the left hand side, the one on the left hand side over here will be actually derivative of the p sub n of t with respect to t, and then you have right hand side. So you end up with the differential equation. Next thing you have to do is, okay, this is the differential equation we just derived, and uh, all you have to solve this equation for p sub n of t. And actually, the whatever I derive is true for the when n is greater than 0. Okay, what happens when n equal to 0? Actually, you can do the same thing. You can find that relationship, okay, between time t and t plus delta t, and then you had actually 0 in the time t, and then see what happens in the t plus delta t, and t plus delta t, two things happens, right? Either 0 in the system or 1 in the system, right? Okay, so you use by observing this behavior, you can actually drive similar. You can drive the differential equation like this. Okay, so you can solve this equation for p0 of t. So n equals 0. Okay, you can find the p0 of t, and when n greater than 0, you can find the p sub n of t. So next following page, actually, okay, this is differential equation with okay, this is true for n greater than 0, right? So n is actually 1, 2, because non-negative actually is integer. I mean the natural number, right? And also we had a differential equation for the n equals 0 case, right? But now the question is, how do you solve this equation? And the solving this equation is not very straightforward. Okay, actually the difficulty coming from this p sub n of t is actually function of time t. The solution, okay, solution depends on time t, right? So actually, if you solve it, okay, if you solve it, you're gonna end up with the very complicated equation like this. This is a function of t, right? So you see actually, okay, this is the I over here. There's the modified Bessel function, okay, and the t over here is function of time t. So it's very complicated function of time t. Okay, so rather than looking at rather than investigating the behavior of the MM1 system using this equation, okay, we want to investigate the system in the steady state. Okay, so what do I mean with the steady state? Okay, what happens to the what happens to the behavior of the system when t goes to infinity? Okay, this is okay. This piece of n of t over here is going to give you the transient behavior. Okay, so like say okay, you have time t. Okay, you wanna look at the p1 over t, for example, when n equal to 1. What do I mean by the piece of 1 over t? Okay, what is the probability that the system has one customer at time t? Okay, so piece of 1 of t is the probability that you have one customer in the system at time t. Okay, that probability might be changed like this. I don't know what it looks like, but something like, let's say something like this. Okay, so like t1 you have the probability over here, you know, t2 you have different probability over here, t3 you have different probabilities. But okay, if you go t goes to infinity, okay, maybe it might be converged, it goes to steady state. Okay, I mean steady state might not exist, okay, but we're assuming that steady state exists. Okay, so if piece of n, okay, if piece of n goes to, you know, converged to the constant, okay, it's not function of time anymore. Okay, which means okay, in steady state, okay, actually derivative is supposed to be 0, right? The system, okay, the piece of n of t is going to be constant, so actually derivative is going to be 0, right? So in steady state we'll be looking at the behavior in the steady state. Okay, so in that case as I okay, if you okay, investigate the solution over here, okay, when t goes to infinity, this is something you're gonna observe. When rho is greater than 1, okay, the probability, okay, remember when rho goes to infinity, okay, then I mean rho is system traffic intensity, right? Intensity is supposed to be actually between 0 and 1, right? If it is either 0 or if greater than 1, okay, this actually this probability, actually piece of n of t is supposed to go to 0. Okay, so steady state, okay, steady state actually okay, what does it mean? Piece of n of t equal to 0 means what? Okay, actually the p0, okay, p0 is 0, p1 is 0, p2 is 0. So for any n, all the probability is 0. So that means no such state exists, right? The system doesn't make sense. System blows up, right? So that's what it implies. Actually, I already discussed that what happens when low traffic intensity is greater than equal to 1, right? So it means that if system, in order to make this system stable, low must be somewhere between 0 and 1. If low equals 0, it doesn't make sense either, right? There's no arrivals. Lambda equals 0, so nothing is coming. So you know, there's nothing to do. So rho must be somewhere between 0 and 1. In that case, okay, piece of n of t will be converged to piece of n, you know, when t goes 0. Okay, so this is a piece of n with the steady state probability of the system size and system distribution, right? So once you know the piece of n, okay, you know the p0, p1, p2, and so on. You know, p0 is probability that in steady state, probability that there is no customer in the system. P1 is probability that there is only one customer in the system. P sub 2 is okay, probability that there are two customers in the system in the steady state, and so on. Okay, right. Okay, in the previous page, I was trying to solve these two equations. The first equation is for n greater than 0, and the second case is when n is equal to 0. And we're trying to solve these two equations for piece of n of t, which is for the mass function for system size at time t, and this is a function of t. However, a lot of times we are interested in the behavior of system size when t goes to infinity. Actually, when t goes to infinity, actually we will be in the steady state, and in steady state, this is not going to be the piece of n of t is not going to be varying with time anymore. So in other words, we can consider this probability as uh, piece of n which is not varying with t anymore. So in steady state, its derivative, because piece of n of t will be constant, so its derivative will be 0, as we discussed in the previous page. So I can consider this derivative equal to 0 in both equations. Then I'll end up with difference equations like this: the first equation and second equation. And here I define the traffic intensity by rho, which is given by lambda over mu, which has been defined as traffic intensity. And using notation for the traffic intensity rho, I can rewrite these two equations like this. And now I have two difference equations, right? So maybe P1 is equal to, okay, from the second equation, P sub 1 is rho times P0, and I can find P2 from the equation over here, P sub 2 in terms of P0, and I can using the first equation, I can find the P sub 3 and so on. So I can solve these equations recursively to find the P sub n. One other way of solving this difference equation is to use Z transform. Actually, the Z transform is when you're given P sub n, actually n starting from 0 to infinity, because n is system size always non-negative number. So you have a sequence of P sub n, which is denoted in the probability of system size in steady state, and you can think about the Z transform of this sequence. And actually in probability theorem, it's called moment generating function. Sometimes it's denoted by MGF. So you're given sequence P sub n, you can find its moment generating function, which is defined like this. This is nothing but the Z transform of the sequence. And the right hand side, actually, I'm trying to find the Z transform of the sequence P sub n. The trick is, okay, let me start with the first equation here. So this is first equation for when n greater than 0. You starting from this is the first equation we have, and I multiply by z to the n plus 1 on both sides. Okay, for the equation, I'm multiplying the z to the n plus 1 to the both sides, and I do a little bit of manipulation. Actually, z to the minus first power, okay, actually times z to the n plus 1. Actually, let's see. Actually, what I did was, actually, this is actually there. I think there's a little bit of problem here. I think this is going to be z to the nth power. Okay. So I multiply the nth power, and no, actually, I think this is right. Yeah, actually, I'm actually dividing by z on both sides again, and I'm ending with this equation, right? Okay, I'm multiplying by this 1 over z on both sides. I'm getting the next line, and then I take summation. Summation over all possible n starting from n equal to 1. As you see over here, I have summation, right, starting from n equal to 1. Then you immediately see that this is Okay, these forms are very similar to Z transform, but it's not a Z transform because the index. Okay, while I'm looking at the summation part, actually we need to have a piece of n to Z to the nth power, right? N starting from 0 to infinity, and but you're starting from okay, you have to change the index starting from n equals 0, right? So you need a little bit of manipulation from the left hand side. uh, so if you're starting with if your summation starting with n equals 0, then you need to subtract this, right? And same thing goes over here. Actually, this one actually you have two terms, right? So this one actually something like this: piece of n z to the n, and n starting from 0 to infinity, and then you have to subtract p0, right? And this is going to be actually z transform piece, piece of n. So, and then you have to subtract p0, right? So this is what it is. Same thing goes over here. So you change the uh, um, you change the indices to be consistent with to conforming to the definition of Z transform or the moment generating function. You do the little bit of manipulation here again, and you get moment generating function of piece of n here, and also you have a moment generating function of piece of n over here, which is over here, over here, over here. And you have bunch of, okay, you have this, the moment generating function here and here, and then you solve these equations for this sub s of z, moment generating function g sub s of z, and you manipulate it and simplify. You end up with something like this. So this is okay. Let me move on to left hand side. You got a moment generating function of p sub n. Now here actually this moment generating function is not complete in the sense that you don't know what the p sub 0 is. However, okay, let's take a look at the definition of moment generating function over here. Why don't you let the z equal to 1, then g sub s of 1 is equal to p sub n and 1 to the nth power, and this is the same as actually p sub n and n starting from 0 to infinity. So what is this equal to? Actually, this we're talking about the sum of all the probability mass function p0 plus p1 plus p2 plus for all powers of p. So actually, your system size can be either 0 or 1 or 2 or all the way to infinity, right? So this sum must be equal to 1 because your system size can be any of these states. What I mean by state is like n equals 0, so which means there is no customer in the system. N equal to 1, there's one customer in the system, and so on. So the point is, this is kind of a boundary condition. Okay, the summation of all the p's will be equal to 1, which actually lead to the condition like this. So when you set the z equal to 1 to the moment generating function, it gotta be equal to 1. So you have moment generating function over here, and you set the z equal to 1, so you end up with this, and which must be equal to 1. So it will give you the p sub 0 equal to 1 minus rho. So now you know what this p sub 0 is. So actually this is p sub 0, which is 1 minus rho. So now you have you have a moment generating complete expression for the moment generating function, and you can actually divide 1 minus rho by 1 minus rho z. You actually do the division, okay, and then you can actually find that this division will lead to the actual summation of actually the expansion in terms of z to the nth power. Okay, I want to actually show that, okay, this division will lead to this kind of expression. Okay, this kind of expansion in terms of z to the nth power. Okay. Now, okay, well, by definition of moment generating function over here, you have z to the n over here. Actually, whatever the coefficient, okay, whatever the coefficient of z to the nth power will be p sub n, right? So this is going to p sub n. What are we looking for is the p sub n, right? System state. I mean the probability system state, right? So we are looking for p sub n, right? So actually we got the solution to the difference equation over here. Okay, we trying to solve these two difference equations for p sub n. So we got an expression of p sub n. This p sub n is actually system steady state probability for the system size. So this is going to tell you that the probability that there are n customers in the MM1Q system in the steady state. Okay, so once you know that this state probabilities, once you know this probability p sub n, you can find the average system size, and also this probability will lead to computing the average waiting time in the system too. We'll continue to discuss how to find average system size or average queue size, and then actually to find average waiting time too. In the previous page, we have derived p sub n, and starting from n to 0 to infinity, and which is actually steady state probability of having n customers in the system. We are currently looking at the MM1Q, which means we have infinite queue size, and we have average arrival rate over lambda, actually Poisson arrival with average arrival rate over lambda, and service time distribution is exponential with service rate of mu. Average actually inter-arrival time, I mean the service time is 1 over mu, right? So what we're interested in right now is the queue size. We are interested in queue size. Actually, let me use the Q, denote the random variable. Q is random variable to denote the number of customers in the queue. And let me use notation S. S is to denote the random variable for system size. What is the relationship between system size and queue size? Is this true? Is system size always one more than queue size? Well, this is true. This is true when n is greater than 1, right? I mean greater than 0, right? When you have when you have say like you have 2 customers in the queue, and which means there must be another one on the service so altogether system size actually S would be 3, right? And Q is equal to 2. However, when n equals 0, this is not going to be true, because if there is no one in the queue, then no one will be under service at all. So this relationship could be either true or false depending on how many are waiting in the queue. Anyways, we are trying to find, in order to find average queue length, we have to find queue length probability, distribution for the queue length. So let me use the notation Q sub n to denote the probability that there are n customers waiting in the queue. So Q is equal to n. And as I said, S would be always greater than or equal to one more, right? One more than the queue size when this is true when n is greater than 0, right? So assuming that n is greater than 0, we have a relationship between Q and P sub n plus 1. So actually if Q1 is equal to, Q1 means there is one user in the queue which is equal to P2, actually 2 in the system. If we have 2 customers waiting in the queue, then we have actually 3 in the system, 2 in the queue and one in the server, right? So we have a relationship like that. Q sub n is equal to P sub n plus 1. And we know, since we know the P sub n, by this relationship, we know what the Q sub n's are, right? We know that Q length distribution. So probability mass function for the Q length. Okay, now how do you find the average system size? Actually, as we know, the piece of n, which is for the distribution for the Q size, we can immediately find average system size, which is expected value of S. As long as you know the piece of n, actually its average will be like this. And remember, the piece of n is equal to 1 minus rho times rho to the nth power from the previous page, right? So you put it in here. So all you have to do is to compute this, right? And computing the summation is not very straightforward, and there will be a lot of different tricks, but one useful trick in the queuing theory will be using the moment generating function. Remember, the moment generating function is defined like this, which is actually given by the z transform of the sequence piece of n. And okay, take a derivative of moment generating function with respect to z. Then right hand side you have this, right? Okay, the expression over here is actually very similar to this one when z equal to 1. Okay, well, you took the derivative and set z equal to 1. Then this is 1. So you have actually the exact same expression as this, right? So the implication is, implication is, if you set you take the derivative of moment generating function and then set z equal to 1, right? Z equal to 1 will give you the average Q length, average system size, right? So LS, which is system size, is same as, which is defined by this, and this is same as actually the derivative of a moment generating function with the by setting z equal to 1. So remember from the previous page, this is our computation for the moment generating function for the sequence piece of n, and you take the derivative of a moment generating function with respect to z, you will get this, and then all you have to do is set z equal to 1. So you have z over here and set z equal to 1. Then you end up with this, and then 1 minus rho cancels out. This is the expression. So you found the average system size, which is actually given by this simple expression. Actually, rho divided by 1 minus rho. LS, which is average system size for the MM1Q, is given by rho divided by 1 minus rho. Actually, it's function of actually traffic intensity. It's only function of only traffic intensity rho. Actually, the graph on the right hand side, actually is drawing this actually you draw if you draw this average system size, you're gonna have exponential function with respect to the rho. Actually, if I draw it, it's gonna be something like this. On the right, okay, horizontal axis you have rho, and vertical axis you have rho L sub s, and when rho equals 0, you have 0, and then actually remember the rho is supposed to be between 0 and 1, right? It cannot be, actually it gotta be less than 1. When remember, the traffic intensity always gotta be less than 1, right? If it is greater than 1, greater or equal to 1, the system will actually go to it's gonna be unstable, right? So actually we have 1, so rho is supposed to be somewhere between 0 and 1, and when rho equals 0, you have L sub s is 0, and then as rho goes to 0, there's a 1, and actually it's gonna be increasing function, exponentially increases like this. Okay, so that implication is as traffic intensity approaches 1, the system size actually grows quickly, exponentially, right? So at the beginning, okay, when traffic load is really small, then the little bit of increase in the traffic intensity will increase the system size a little bit, but rho is getting bigger and bigger. Okay, then average system size grows exponentially, quickly it grows. Okay, now let's take a look at average queue size. Okay, well, you might guess that the queue size, I mean queue length and the queue size or queue length has something to do with system size, right? Because actually Q, I mean S is always uh, uh, one more than Q size, right? When n is greater than zero, right? So this is a relationship, right, between the Q size and system size. And anyways, in order to find the average Q length, you need the expected value of you need to find the average Q size. You need the distribution of the Q length, which is Q sub n. So we have Q sub n over here. So this is the average, and then Q sub n is same as P sub n plus 1. And so, okay, this is the expression we want to evaluate. And by changing the variable, actually starting from n equal 0, but maybe you can set n plus 1 equal to k. Then actually I'm changing variable. Okay, so now I'm using notation k, index k, and so now this is k minus 1. Then actually this summation split into two terms. And as you see over here, the very first term over here, actually is, as you see over here, this is actually same as ls, which is ls is average system size. And you have remaining term over here, and you can actually, this is summation of all the p's except the p equals 0. I mean, except the p sub 0, right? Because the index starts from k equal to 0, k equal 1. So this is actually, because actually the p0 plus p1 plus p2 plus all the way equal to 1, right? So actually this is summation from the p1 through the p2 all the way to pn. So this summation is equal to 1 minus p sub 0, which is 1 over here. And remember that actually in the previous page, actually we have shown that actually p0 is equal to 1 minus rho. So actually this term is equal to 1 minus p0 is equal to rho, right? So this is going to be rho. So therefore my final expression over here is L sub q is equal to L sub s plus rho. So L sub q is equal to L sub q is equal to L sub s minus rho, or L sub s equal to L sub q plus rho. Okay, this is the expression I just got. Okay, so I got L sub s equal to L sub q plus rho. Okay, well, this is a very interesting result because okay, well, we know that s is equal to q plus 1 when n is greater than 0, right? But this is only true when n is greater than 0. That means okay, you take the expected value of this when n is n is greater than 0. Okay, expected value of this and expected value of s. So expected value L sub s equal to L sub q plus 1, always greater than 1, right? However, it depends on whether n is greater than 0 or not, right? So as we well, the number of customers will be the random variables. So on the average, the average according to our expression over here, I mean derivation over here, L sub s is equal to L sub q plus rho, not the 1, okay? Because rho, I mean whether n is greater than 0 or not, okay, it depends on the traffic intensity rho. So that's why our derivation is telling you that L sub s is a little more than L sub q. Actually, how much actually depends on traffic intensity. Okay, this is extra. Okay, extra the traffic on the top of the queue size. Okay, so system size is queue size plus average queue size plus traffic intensity. Okay, so we got the in the right here we found the L sub s here. So you subtract the L sub q is L sub s minus rho. So L sub s is found over here. So you subtract the rho from here, you get this. Okay, so this is this is expression for the average Q size. And if you draw it again, actually it's going to be exponential function like this. When rho is approaching 1, it goes to infinity again, right? And well, as I said in this figure, I'm telling, okay, when rho increases approaching approaching 1, also as system size goes to infinity, right? So Q size goes to infinity too. When rho goes to 1, it's asymptotically goes to infinity, right? But actually the only difference is actually that you have square over here and you have rho over here. So depending on whether you have first power or second power in the numerator, the graph will be a little bit different, but very similar in its behavior. Actually, the behavior of approaching infinity as rho goes to 1. Okay, so we have so far I have derived average Q length, and average. Actually, I found the average system size and average Q length. And in the following page, I'd like to discuss the relationship between the Q length or system size or Q length and the waiting time. Well, actually, intuitively you can imagine that the waiting time in the system or Q actually queuing delay, okay, queue time, okay, how long you have to wait in the queue will be highly related to the system size or queue length, right? I mean, the longer the queue length is, the longer you're gonna wait in the queue. Or the larger the system size is, the longer you have to wait in the system, right? There must be obvious relationship between those two, and we're trying to find what kind of relation they have. Okay, now I'll start talking about waiting times. We want to analyze how long we have to wait in the queue or in the system. Before I talk about the waiting times, let me introduce two useful terminologies we often use in analyzing the communication network. One is utilization factor, the other is throughput. These are the terminology frequently used. Definition of utilization factor is probability that server is busy. What is probability that server is busy? Actually, if you find the probability that server is not busy, which means idle, then actually one minus probability that system is idle will be the probability that server is the busy. Actually, when you don't have any customer in the system, so in other words, n equals 0 in the system, then the server will be idle. So P sub 0 is probability that server is idle. So 1 minus P0 will be the probability that the server is busy. So 1 minus P0, which will be the utilization factor. Actually, P0 actually has been derived as 1 minus rho, 1 minus trap intensity in the previous page, right? So if you subtracted 1 minus rho from 1, actually 1 cancels, so you have rho. Okay, it happened to be, okay, actually the utilization factor happened to be same as the traffic intensity, right? So by defining the utilization factor as the probability that server is busy, then it is same as traffic intensity. So traffic intensity is telling you that the probability that server is busy, and which is actually utilization factor. And how about throughput? Okay, throughput is average departure rate. Okay, you have actually MM1Q, for example, and Poisson arrival, and you have service rate of mu, right? Arrival rate of lambda and mu, given lambda and mu for the arrival rate and the service rate. What would be the departure rate? Okay, well, if you don't have anyone in the system to know there's no departure, right? Otherwise, if there is someone waiting in the queue, and if there is someone under service, then actually the service rate will be same as departure rate, right? Everyone served, uh, uh, the customer. Okay, as soon as the customer of the service for the customer is done, the customer will leave the system there. So in that case, service rate will be the same as departure rate. However, sometimes the system would be in the stage zero, right? In that case, there's no departure. Uh, so it's not okay. This is not obviously true. Uh, I mean the when the I mean the departure rate is not equal to mu. Okay, departure rate is not going to be same as mu. Then what is average departure rate? Well, uh, actually you have when you have okay well uh, uh, the okay you have utilization factor which is rho, and so this is a probability that the server is busy. When server is busy, the departure rate is mu, right? When server is not busy, departure rate is zero. So actually average departure rate is zero times um, 0 times 1 minus rho plus 1 mu times actually rho, right? So this is actually this is when n equals 0 in the system, when this n is not equal 0. Okay, when n is not equal 0, actually departure rate is same as service rate, and the corresponding probability is rho. And 1 minus rho is probability that server is idle. So when the server is idle, the service rate is actually 0, right? So this is 0. So actually this is the same as mu times rho, which is what we have. And the mu is lambda divided by mu, so cancels out, and you have lambda. Interesting. This is a very interesting result, right? The average departure rate is same as average arrival rate. Okay, if you have arrival rate of lambda in the system, then average departure rate is actually average departure rate is actually same as arrival rate. Okay, this is interesting observation we have for the MM1 queuing system. Now, next thing is to drive the waiting time. And in order to find the average waiting time, okay, well, we have two different kind of waiting times, right? One is waiting time in the queue, and the other is waiting time in the system. And in order to find the waiting time distribution, I mean, in order to find the average waiting times, you need to have the waiting time distribution. Okay, so let me introduce the random variables WS and WQ and Z, three different random variables. WS is random variable for the waiting time in the system, and WK is waiting time in the queue, so which is actually queuing time. And Z, as usual, Z is random variable to denote the service time. Okay, we have three different random variables here, and the obvious relationship between waiting time, the system waiting time, and the queuing time is this. Actually, this is a queuing delay. Average. This is WQ is random variable for the queuing delay, and Z is service time, right? So the total waiting time in the system will be waiting time in the queue plus service time. So we have relationship here, right? WS is equal to WQ plus Z. And what we are looking for is distribution for the system waiting time WS. This is CDF, right? This is CDF for the WS. This is CDF for the WQ, right? So we want to find the CDFs for the system waiting time and the queue waiting time, queuing delay, queuing time. Okay, actually the queuing time over here is the same as queuing delay. So we want to find these distributions. And once you know these distributions, and you can immediately find their average, right, using the PDFs. Now let me start talking about waiting time distribution. In order to compute the waiting time, average waiting time, we need to find the waiting time distribution. And we're still looking at the MM1 queue. Actually, we have an infinite size of queue and a single server. And we have Poisson arrival rate of lambda, and service rate of mu. Actually, this service time distribution will be exponentially distributed with mean service time of 1 over mu, right? That's what MM1 queuing system is about. And let's say, in order to find waiting time distribution, let's say there is one customer. Let's focus on one particular customer, which is called the test customer. Test customer, which stands for okay, well, actually TC stands for test customer, and we like to focus on this particular customer. And let's say, okay, when this test customer is arriving into the system, he finds n customer in the system. N is the number of customers in the system ahead of this test customer, and n can be 0 or 1 or 2, right? So in other words, the test customer finds n customer. I mean, that is okay. And when n equals 0, okay, that means test customer find no one in the system, right? So as soon as he arrives in the system, he will be immediately served because no one is no one is in the system, right? When n equal to 1, actually, when he arrives in the system, there is one customer is under service right now, right? If it is 2, when n equal 2, then 1 is on the server and 1 is waiting in the queue, so he finds 2 ahead of him. Anyways, depending on how many customers waiting in the system, the waiting time of the test customer will change. So the waiting time of test customer will depend on how many customers are waiting ahead of him, right? So this is the distribution we like to find. At WQ is actually, you say, okay, WQ is the waiting time for the test customer. And of course, we're going to assume the first come, first served. And here the x, okay, is supposed to be waiting time, so it's going to be non-negative. So this distribution, okay, this distribution CDF can be represented by in terms of the conditional probabilities, right? So depending on how many customers are waiting ahead of him, we're gonna have different distribution, right? So distribution is conditioned on the number of customers in the system when the test customer arrives. So P sub n is probability that there are n customers in the system. So when there's a probability that, okay, given this probability and given n customer in the system, we want to find its distribution. I mean, it's service time distribution. I mean, waiting time, the queuing time. So this is so like when. So I can actually split this summation into two cases, when n equal to 0 and when n is greater than 1. When n equals 0 means no one is found ahead of the test customer, so the corresponding probability P0, and when there's no one ahead of him, so the probability that WQ is less than X when test customer find n equals 0. And this probability, okay, is gonna be obviously 1, right? Because always, since there is no one ahead of the test customer, so no one is in the queuing system, so the waiting time, okay, the waiting time is actually always less than waiting time is 0, right? Because the test customer is going to be served immediately, so this event will be actually the WQ is 0, so it's always less than or equal to X, so this probability is equal to 1. And when n is greater than 1, so this is the case, right? This is the case when n is equal to 0. So this is equal to actually P0, right? This is the P0. And when n is greater than 1, so including 1 to all the way to n, so Pn times this probability, right? This is a probability that the distribution of the queuing time when test test customer finds n customer in the system. So let me use notation k sub n. K sub n is the corresponding conditional probability. Okay, so now our task is all we have to do is to determine to find the conditional probability k sub n. Okay, if we do know the k sub n, as we know the p sub n, right? We know the p sub n, and this is p sub 0. We do know what p sub 0 is. So all we have to know is k sub n of x, which is this particular conditional probability. And now let me use. Okay, well, let me draw the timeline. Okay, t, and let's say this is time 0, and let's say this is arrival time for the first customer. Okay, actually we have actually what I mean by the first is as we have n customers in the system right now. So among all those n customers, this is the first one, and then there is another one. There is another one. So and then we have actually n customers in the system, right? And then we have a test customer arriving here. So T1 will be the service time for the customer number 1, and we have another service time for the customer 2. This is a service time for the customer. Well, actually, I have to use different. Okay. I think this. Okay, this is service time for the customer number 1. So let me use T1 to denote the service time for the customer 1, and then customer number 2. There is service time for the customer 2, and I have T3, and then I have actually T sub n, right? After T sub n, test customer will be served immediately, right? So total waiting time will be actually from here to here, which is actually some of the service time for all the customers ahead of him. So we have to add all the service time for all end users, all customers. So this is this is actually definition of T here. T is the sum of all the service time for all the customers ahead of the test customer, and we know that all these T's, the service times are actually IID actually exponential distribution, right? Independent. We know that they are supposed to be independent, and all they're supposed to have all same exponential distribution, right? So so all these T's are IID exponential distribution. Okay, so now all we have to do is in order to find the CDF, you have to find the probability that T is less than or equal to X. So the question is when we have IID T sub i's, I is 1 to n. What is this distribution? What is the distribution, or what is CDF of some of the exponential distributions? Okay, that actually probability will be CDF for this CDF for the capital T, and which is actually same as k sub n of x. So in the following page, we're trying to find the k sub n of t, which is CDF for the capital T, which is sum of the n independent exponential random variables. Okay, in previous page we have defined capital K sub n, which is defined as conditional waiting time distribution for test customer, which depends on the number of previous customers ahead of the test customer. And we have shown that actually this K sub n of x is same as probability that T is less than or equal to x, and the T over here is sum of the n independent service time, the service times, right? So these are the service time for all the customers waiting ahead of the test customer, and we know that these are independent random variable, and they all have the same distribution, which is actually exponential distribution, right? So, from the probability theory, we know that PDF of the sum of the independent random variable will be actually PDF is given by the convolution of the individual random variable, the PDF of individual random variable. In other words, okay, let me use lowercase, okay, lowercase of the lowercase to denote the PDF. So the case of n of x is PDF of the capital K over here. This is CDF. If you take a derivative of capital K, we get this lowercase case of n, which is PDF of capital T. And as I just said, it's going to be given by the convolution of the individual random variable, individual independent random variable. So this is PDF of the T1, this is PDF of P2, and so on, and they are all given by the convolution because they are all these random variables independent, and each of these PDF is given by the exponential, right? And they have this all same identical distribution. So I have actually n exponential PDF convolved with each other, and so if you convolve this exponential function n times, actually you're going to end up with this expression. I'm not going to drive, but you can show that convolution of n exponential PDF will end up with this particular expression. So now I got the PDF of actually PDF of the capital K and the CDF, and if you take if you integrate the PDF, you're gonna end up with the CDF, and this is the expression. I don't think this summation is it's not straightforward to evaluate this integral, but if you look at the further development over here, a lot of computation will be reduced to the simple expression. Okay, well, let's go back to this CDF. Actually, CDF for the waiting time. I'm CDF for the waiting time for test customer, and so actually we can split into two different cases, right? When system is empty, and the other is when system is not empty here. So when system empty, this probability actually is given by this. Of course, no one is waiting in the system, so the waiting time is 0, which is same as P0, right? And over here, actually, we just found capital case of n over here, and which is multiplied by the p sub n, and p sub n is actually probability that we have n customers in the system in the steady state. Okay, which this is something we have derived for the MM1Q previously, and then whatever the integral over here actually is the one we found over here. Okay, now this mathematical expression over here looks very complicated, but a trick over here is actually you actually take this integral out of the summation. You're gonna have this. So now the summation is inside this integral, and it is interesting that the expression over here, right over here, okay, actually this is actually same as this is actually expansion of the exponential function over here. You can check it out, okay. Okay, any exponential e to the x can be represented by the actual summation of m factorial to the x to the nth power, right? 0 to infinity, right? So you're using this kind of expansion. This summation can be represented by the exponential function over here. Then we have two exponential functions over here, one over here, and then they can be combined into one. And now, okay, this integral over here can be this integration of the exponential function, which is I mean the evaluation of the this integral is straightforward, and the rest of the computation are very, very straightforward, and you're gonna end with this simple expression over here. This is actually the CDF for the waiting time. That's something we've been trying to compute. So once you know this CDF, you can actually, if you take derivative with respect to x, you can find PDF for the waiting time, and you can, of course, you can compute the average waiting time and so on. Okay, we just got the CDF of queuing time WQ, which is given by this, and actually this is the expression for the CDF. And if we draw the graph of this CDF, okay, it's function of x and FQW of WQ, FWQ of x, actually when x is less than 0, actually it's 0. And then when x equals 0, actually there is, okay, when, okay, you plug in x equals 0 in this this expression, you actually going to have 1 minus rho. So when x equals 0, you have 1 minus rho. And then x is greater than 0, actually you're going to have graph. And when x goes to infinity, it's going to approach 1, right? So the graph is something like this. So actually the whole graph looks like this. And in fact, there is jump. There's jump at x equals 0, right? So if you take derivative of the CDF, which will give you the PDF, and due to this jump, actually you're going to have delta function for this PDF. So the first time you look at this PDF, you might be wondering where this delta function is coming from, and actually it's coming from this discontinuity here. So once you have PDF of queuing time WQ, you can find the average queuing time, right? So expected value of WQ is expected value over here, actually, and you go through this computation. Okay, I think that this computation is very straightforward, and I want to go line by line. And if you go through all these lines, you're going to end with this simple expression. So this is actually expression for the average queuing time for MM1 queuing system. And again, okay, you see that this waiting time, I mean that this queuing time is full function of traffic intensity. And again, okay, this waiting time, if you graph this waiting time distribution, I mean the average waiting time as function of rho, okay, expected value of WQ is actually rho is between 0 and 1, right? And when rho equals 0, actually you have 0, and then rho approaches 1, it's going to be exponentially increasing. So the larger the traffic intensity is, the much larger that the average queuing time will be. Just like waiting time, right? Average, I mean the average, just like system size, or just like we have found we have seen the similar observation for the system size, right? So average queue length will be exponentially increasing when rho approaches 1. So it is a very, I mean, they are actually the queuing time, the waiting time in the queue, which is the queuing time. The queuing time is of course closely related to the system size, right? The longer the system size is, I mean, the larger the system size is, or the longer the queue length is, the larger the average queuing time is. So all these results are very consistent. Okay, we just have looked at the average queuing time, right? How about the average system time? Okay, so what I mean by the system time is waiting time plus, okay, once you wait in the queue, and then there will be a service time, right? So your system time will be sum of the waiting time plus service time, which is okay, denoted by WS. WS is service time, and it's average, okay? It will be expected value of WS. And so if you take expected value of WS is the sum of the expected value of WQ plus expected value of the Z. Z is actually service time, right? So we just found the expected value of WQ, which is given by this, and expected value of expected value of service time is 1 over mu, right? So this is something we find over here. Okay, and then 1 over mu added, and you end up with this. This is average system time. Okay, the same thing goes here too. When rho goes to 1, okay, still we get a very this graph actually will be actually something like this, right? When rho approaches 1, average system time goes to infinity, right? Dramatically increases, right? Exponentially increases, right? And also you can find PDF of system time. Okay, here actually we have looked at the PDF of the queuing time, right? Using using this relationship, you can find PDF of the system time, right? Actually some of these two random variables and these two random variables are independent of each other. So PDF of some of the two independent random variables will be given by the convolution of the individual random variable, convolution of PDF of individual random variables, right? So we have PDF for the WQ, and we have PDF of the service time, which is actually exponential distribution, exponential PDF, right? So using the fact that, okay, you know that the PDF of service time, the exponential service time, and you have the PDF of the WQ, and if you do this convolution, you're going to end up with this. And the interesting thing is this is also exponential distribution with this particular parameter. Okay, so in other words, okay, the system time. Okay, system time WQ. WQ is WQ. WS, I mean system time WS is following the exponential distribution. Okay, that's interesting observation here. We just have derived the average system size and average waiting time for the MM1 queuing system, and let me summarize the result. The system's average system size given by this, and average queuing size, Q size, LQ, is given by this, and we also derived the waiting time, right? System waiting time and Q waiting time, Q time. There's a queuing time and there's a system time. Okay, so these are the expressions we just have derived, and using these expressions we can compute the performance of the given queuing system. For example, this is a very simple example. We have a switching system that can be modeled by the MM1 queue, because we have in here actually we're assuming that there is only one server. Okay, and we have Poisson arrival. Poisson process. Arrival is following the Poisson process with average interarrival time of 800 milliseconds, which means 1 over lambda actually is interarrival time actually is 1 over lambda, right? So this is 800 milliseconds. And also tells you that the service time is following the exponential distribution, right? With service time of 500 milliseconds. So 1 over mu is average service time, and which is given by 500 milliseconds. So this this example is actually describing the MM1 queue, right? Okay, the arrival is Poisson, and service time the service time is following the exponential distribution, so it's MM1 queue system. And given 1 over lambda and 1 over mu, actually rho is actually lambda over mu, which will give you the actually 500 over 800, which is 5/8. So once you know that the traffic intensity rho, the question is to find what is the okay. You're looking for the average waiting time. Okay, when we say average waiting time, we have to make sure that we talk whether we are talking about average system waiting time or queue waiting time. Okay, queue waiting time is the queuing time, and system waiting time is system time. Okay, let me just assume that the waiting time over here is system waiting time. Okay, so what is what is the average system waiting time? Well, here I'm using the different term delay. Delay is still like same as waiting time, right? So average delay or average system time is given by this, and we got this expression, and we know what the rho is, and right here, and we know what the mu is, right? Actually, 1 over mu is 500 millisecond. 1 over mu times 1 minus rho, which is 5/5, so it gives you the more than I think the unit is milliseconds, so this is more than 1.3 second, right? 1.333 second. Okay, now what if we change the service time? Here actually the switch. Okay, this is a switching system router. Okay, for example, and the server has much faster service. So the average service time is reduced to 400 milliseconds. It used to be 500 milliseconds, right? Now service time has reduced to the 400 milliseconds, which means it's faster. The switch is faster. So the the average service time is reduced to 500 milliseconds to 400 milliseconds. And so if you use 400 milliseconds for the actually this is I think this typo, this is actually 400 milliseconds, right? Okay, and then you compute the average system time, the delay, average system delay turns out to be 400 milliseconds. So actually it has been actually the delay has been reduced by almost 1/3, right? It used to be 1.3 millisecond, 1.3 second, and now it's 400 milliseconds. So it has been by reducing the service time, right? By employing a little faster switch, the waiting time has been reduced by 1/3, almost 1/3, right? So this is the one simple example to illustrate how we use the result. Okay, now we just if this table is summarizing all the results that we have derived, and if you look at the if you look at relationship between system size and delay. Okay, this is system size, and this is system delay, right? Okay, what is the relationship between these two? Okay, they are very closely related to, right? You see that the one minus lambda here, one minus rho here, one minus rho here, right? Actually, if you multiply lambda to the waiting time, average delay, you're gonna end as lambda divided by mu is rho, right? So if you multiply average arrival rate by the average system time, the delay, you're gonna have average system size. Okay, so actually we get this relationship. LS, which is average system size, is same as average system delay multiplied by the average arrival rate, right? This is the relationship between these two quantities. You multiply by lambda. Same thing goes to the Q length. This is the average Q length, right? LQ. And if you multiply the delay, average delay by lambda, you get the LQ. So you multiply by lambda, right? Lambda divided by mu is rho, right? So rho times rho is rho squared. So you get that expression, right? So we just got the relationship here. We got something like this. L is equal to lambda times expected value of W. So L is average length, either system or Q, is always lambda multiplied by the waiting time. So waiting time, average waiting time multiplied by the arrival rate will give you the average length, Q length or system length. Okay, this particular relationship, particular relationship between the Q length or system length with waiting time or delay is called the Little's formula. This is a very, very useful formula to use for MM1 queuing system. So my conclusion is, my conclusion is this particular expression. We have L is equal to lambda times W. Okay, let me use the bar to denote the average. So this is either Q length or system length, system size, which is multiplied by which is given by average waiting time multiplied by the lambda, right? So if you do know one of these two expressions, if you do know L, you can find the W. Or if I give you W, you can find L, right? So this is a very useful expression. In previous derivation, I independently actually derived the L and the W, and then we found the relation between these two, which is given by this Little's formula, right? However, if you do know the Little's formula, actually, you don't have to derive L and W independently. Once you know only one of them, you can find the other one. Okay, that's the beauty of Little's formula, and this Little's formula is very useful for the queuing theory, and actually I have justified this Little's formula for MM1Q. However, Little's formula is actually way more general, uh, in the sense that Little's formula doesn't involve any particular arrival or service distribution. Actually, my derivation for Little's formula in the previous page is based upon the assumption that we have Poisson arrival and exponential service time distribution, right? But this relationship, this formula is still true for any type of a queuing situation. Okay, as long as lambda is average arrival rate, and then as long as this lambda is average arrival rate for anything that enters into the system, this equation is still true. Okay, that's a beauty of I mean the generality of this. I mean the Little's formula is general enough. Okay, all right. So maybe for the rest of the semester, I mean the rest of my queuing theory, if you're asked to find the average waiting time, then all you have to do is to find the average queue length and then divide it by lambda. Or you drive if you ask to find the queue length, you drive the waiting time, average waiting time, then you multiply by lambda. Then you immediately know what the average queue length over average system length. Okay, on the right hand side, I'm trying to justify this Little's formula. This is not rigorous, but still, like, it's gonna be good. It'll give you really good intuition. And I don't want to discuss these details here. And I still just want to remember this result. Okay, let's say this is the queue, and we have server and arrival and the departure. And let's try to find the probability that you have actually the system size is k. So how do you find this probability? Can you estimate this probability by observing the system? Okay, well, actually, this is what I'm gonna do. Okay, this is timeline, and then I watch this system for 24 hours, for example, and then I find that I have k. I have k over k customers in the system during this time period, and there's another time period during which I have k customers in the system, and there will be another interval, okay, during which I have k customers. So let me use the notation like say this is T1 of k, this is T2 of k, and this is T3 of k, and so on, right? So these t's are actually the length of the interval during which I have k customer in the system. So I observed this system for a long time, and let me use actually the t is the time, the observation time, and if I take a limit, okay, limit goes to infinity. Actually, I observed this system for a long time, and actually, if I sum all the interval during which I equal to 1 to infinity, okay, divided by capital T. So actually, the numerator, actually, I'm adding all these intervals, right? Adding all these intervals, and divided by the whole interval actually will this uh, this quantity over here. This quantity is going to tell you that the proportion of the intervals for the uh, for the situation when you have k customers. So maybe this limit, okay, this quantity will be same as this probability, right? So this is time average, and this probability over here, okay, this probability is actually going to be same as this, right? The time average will be this probability that the system size is equal to k. Okay, and there will be another situation. Okay, let's say you have a customer just arriving in the system. Okay, this is a well, so you can say you can call this customer test customer. So we have test customer arriving into the system, and then observe how many customers are waiting in the system. So maybe you can find the probability that there are k customers waiting in the system when test customers is arriving into the system. So this probability, okay, actually let me use this probability q k of t. Okay, I'm trying to use this this probability to denote the probability that I find k customers waiting in the system when I'm arriving into the system at time t. So now my question, okay, and let me use, okay, well, let me use the different notation for this. Okay, let me use a p sub k of t. Okay, this is my notation for time average. Okay, this is time average, right? So for the time average, I'm using the p sub k of t. Okay, now my question is a p sub k of t, is p sub k of t is equal to, my question is p sub k of t time average the same as q sub k of t. I just defined two different probabilities, right? Are they equal to each other? Okay, well, let me redefine here. Okay, p sub k of t is, okay, probability that system is in state k at time t. So state k means k customers waiting in the system, right? In the system. That's p sub k. Q sub k of t is actually the arrival at time t finds the k customer in the system. The system is in state k. So I like to check whether these two probabilities are equal to each other. Okay, well, just take a look at the simple example here. Okay, let's say we have a deterministic arrival. Okay, actually every 10 seconds I have arrival. So okay, right here I have arrival, and then 10 seconds I have arrival, 20 seconds I have arrival, 30 seconds I have arrival. Every 10 seconds actually I have arrival, right? And then service time is also deterministic. I have service time of 9 seconds. So the first one departure here and second one departure, right? Every 9 seconds actually we have departure. So if you look at the whole timeline, you find that actually you find that one customer in the system during this interval, one customer during this interval, another one, okay, interval over here, one customer here. So actually you find that 90% of time there will be the one customer in the system, right? So in other words, P1 is equal to 0.9. Okay, P1 stands for actually P1 stands for probability that we have one customer in the system on from the time average point of view, right? If you look at the time average, if you actually compute time average throughout the period, okay, it's 90% of time we're going to have one customer in the system. However, okay, well, how about Q1? Okay, what is Q1? Q1 is by definition over here. Q1 is actually a probability that the arriving customer find the one customer one in the system. Okay, any arriving customer finds one customer waiting in the queue. So in this case, the customer already departed at in 9 seconds, and then the new arrival, okay, the one customer, the newly arriving customer, okay, find no one in the system, right? So the system is always empty when customer is arriving. So actually the Q1 of Q sub 1 is always 0, right? The probability is 0, right? There is always the system is always empty when customer is arriving. So the probability that there is one customer waiting in the system is going to be 0. So my point is these two probability P1 and Q1 are not equal to each other. So this relationship, it does not hold, right? They are not equal to each other. These two probability are not equal to each other. However, okay, my conclusion is when arriving, the arrivals are Poisson, okay, when the customers arriving by the Poisson process, then these two probabilities are going to be equal to each other. In other words, time average is same as the probability that the arriving customer see a K customer in the system. Okay, so we actually this is very interesting and useful property. Okay, what's called the Pastat property. Okay, pasta actually coming from the P here, A, S, T, A, and Poisson arrival C time average. Time average is actually same as this probability piece of K of T, right? And the Poisson arrival, okay, the arrival, okay, actually find K customer in the system ahead of him, actually given by this probability, right? So these two probability, the Poisson arrival C, this time average, this is Pastat property, and so this is going to be very, very useful and an interesting property you might want to come across with in the queuing system, queuing theory, and we can actually prove this. This Pastat property can be proved by a couple of lines actually. Here, actually, Q sub K of T is actually defined. This is by definition of the Q sub K of T. We have actually interval, right? We have actually, let's say this is T. I have another. This is let's say like a tiny interval delta T, and the customer is arriving to this interval delta T. Okay. When I arriving during this interval, then this interval is delta T goes goes to 0. So when I'm arriving during this interval, and the probability that I have K in the system ahead of me, right? So I mean that the arriving customer finds K in the system, and this is a corresponding probability, right? And using the basis theorem. This is a basis theorem for the conditional probability over here. Actually, this is basis theorem, okay, for this conditional probability. And using, okay, well, can you see the this is true. Actually, what this okay, well, you have by time t, before time t, okay, by time t you have K in the system, and then this is a probability that this is actually event that you have arrival in this interval, right? Actually, the arrival in this interval is independent of the number of customers in the queue by the time t. So actually, I can remove this condition, right? I can remove this condition because these two events are independent, right? So this is same as this. So actually, I can remove this condition, and then so these two probabilities cancels out. I end up with this, and this is P sub K of T. Okay, this is proof for the Pastat property. I have another example here, and you can actually show that Pastat is not applicable to this kind of this discouraged arrival. What I mean by discouraged arrival is, okay, you have a Poisson arrival. Okay. However, this is discouraged arrival. So, like, what I mean by discouraged arrival is, if arriving customer find that there are too many users in the system, too many customers waiting in the system, maybe he doesn't want to join the system, so he doesn't get into the system simply because the customer is discouraged. So, which means arrival is not Poisson anymore, right? Even if the customers arriving by the Poisson process, but some of them will be doesn't actually get into the system due to the discouragement. So the effective arrival is not Poisson anymore. So therefore, the pasta is not applicable. Right? Pasta is applicable only when we have Poisson rival, right? Okay, so in this case, discouraged rival is not Poisson rival. Okay, so if you compute the P sub k of t and Q sub k of t, they are not equal to each other in this case.